Welcome back to my YouTube channel. So, I'm back after a long break away. I hope everyone is well before I begin here. So, back in early December, just when I uploaded part 1 of this new project, I fell ill with a flu virus. I thought I was getting better within a week of taking it, but it came back worse with a chest infection by mid-December. So it floored me all over Christmas, right through the new year and into mid-January. So I have just recently regained enough energy to do this video that I had promised Len for around mid-December. So it's been the longest running gap throughout my YouTube channel, approximately just creeping over 2 months. Over the past couple of weeks, I have put together a lot of interesting material that covers vast detailed designs of this new project. Okay, so this project is one of my most special pieces that I created 10 years ago when I was 27 years old. If you haven't already, please see part 1, What is an Aperture? My Aperture introduction, the last video that appeared on my channel. Part 1 basically gives an insight on what exactly an aperture is before I started diving into the deeper depths of this project. So it's basically a brief introduction into an aperture from a photography perspective, whilst also using the human eye biology to explain the different similarities. For example, in that video I discussed how our pupils act as a natural aperture, increasing or decreasing in diameter to capture light from our surroundings as needed. In the in-depth discussion that follows, I will discuss my earlier prototype to the final prototype design. To be clear, this video part 2 shows 2 separate models, 2 separate prototypes of my aperture, each with different iterations of various components. The first prototype was created a long time ago, whilst the second prototype was reverse engineered from the first prototype. Because of the vast amount of information that follows throughout this video, I thought it would be best to make a video to present the actual project masterpiece in later date. So I have named it the masterpiece throughout to avoid confusion from it and the 3D models. I don't want to take anything away from it, Len, bombarding everyone with detailed design information during the final presentation that will appear in part 3. So I'm getting this all out of the way now in part 2. Therefore, part 3 of this project will follow in due course and will be demonstrated with great satisfaction, considering the amount of dedication given to the different approaches to design and manufacture the final prototype system. Hopefully, if the weather picks up within the next 4 weeks, the video will be set in a distinctive place to match that of the project, as it deserves such an awesome background. Doing projects like this is to show difference worldwide by bringing uniqueness, distinctiveness, rareness, and to basically just to put myself out there, so enjoy. One final comment here. It's to demonstrate what can be achieved by a single individual at home, aided on by envious behaviour, negativity from some outsiders looking in. Anyway, enough of that. I will jump straight into this now. Okay everyone, so here is my first 3D model, which I produced a long time ago. So this was the foundation for my initial prototype, from which I generated numerous drawings from to help with the production process. So before I move into the finer detail here, I want to give a brief discussion on what we see on the screen. So if I scroll around to this side of the aperture, we can see the front face highlighted in the blue. So I call it the front face as it's the side I have designed and select it to be mounted on or to the outside of a building, door or wall. So this is the exterior side, and the side with the removable cover is the interior side. So if I was to mount this unit into a wall, this front face of the Aperture could be made flush with the exterior object. For example, that being a wall, or the gable of a house, or the gable of a garage or shed. So I have designed this base enclosure, the surround, also known as a surround, to be compact for this reason, at only 100mm wide. So that's from this face to this removable panel face. So all you would see if the system was used in this case is the outer surround and the diaphragm shutter. So this part, the 18 blades making up the diaphragm, and this face, and also this face. So it doesn't need to be flush. This is just a general description of what can be done with my unit. So the front face is designed to be secure, meaning it's welded completely and no stainless fixtures exist here. So between this point, this face and this face, it's welded, and also this face and this face is welded here, this joint here. So there's also no visible mechanisms or mechanical linkages or anything displayed. Nothing can be seen here. So everything is hidden behind this enclosure, which is important to the harsh environment. So this also benefits the visual look of the system, as you will see in part 3, the masterpiece, when I upload it to my channel in approximately maybe 4 weeks, depending on how my health holds up. So I have a lot to discuss here, but one last thing before we move on. The system could also be used internally indoors. It's not restricted to outdoors, even though I've designed it for harsh environments. So what I'm going to do here now is I'm going to run a little animation of the Aperture working. So this is just going to be a little insight into it. I'm not going to go through it in detail just yet, but I'll run it here now, just to give a little demonstration to make things a bit more interesting. So here we go. So opening, closing, opening, closing. So you get the idea. So back to the model now, and we're going to keep continuing talking about this. So I will get back to the animation later. For now, I'm going to continue this in-depth discussion, and to begin, I'm going to remove, suppress the interior cover to uncover the mechanical assembly. So let's first get back around to the interior side. And what I'm going to do here is I'm going to suppress the cover and also remove this rubber edge trim that's placed on the inner edge of the cover. So some may notice my Aperture is designed completely different from your usual Aperture within a camera. So in early prototyping, I was going to develop a system with a large control ring with multiple linkages to control the blades and leaves of the diaphragm. This would be your common control mechanism of an iris diaphragm seen within a camera Aperture, although I decided to do this project a little different by using a large ribbed belt and gears to control the diaphragm instead, just to be different, to be creative. So this tended to be more difficult than first imagined, as you will see why soon, come part 3 on my channel when I upload the video of the real piece, the masterpiece. So I initially designed it this way for many reasons, such as to reduce complexity, whilst also reducing the cost and the weight of the Aperture louver system. Also in my mind, less mechanical moving parts or points meant less mechanical wearing parts. So I mentioned louver system there, so that's just another term that I'm using to call my system here. So Aperture louver system. Okay, so before I dive deeper into this model, my model, I want to touch to describe more concisely on how the control mechanism within your typical camera aperture works, mainly so others can appreciate the difference with my system. So what I'm going to do here now is draw the control ring in black over my aperture near the perimeter. So I'm going to set the ring, I'm going to set it bold and black. So here we go. Okay, so I'm not happy with that one. Okay, so that's not bad. So just to make it clear here, the large control ring usually surrounds the perimeter where the control ring moves freely in both anti-clockwise and the clockwise directions. So several control arms, depending on the number of blades within the diaphragm, are connected to this ring, and the blades at the focused pivoting points. So we'll set pivoting points. So what I'm going to do here now is I'm going to draw a few of these arms in red over my aperture, where sometimes these arms are shaped like bananas and sometimes they're straight. For this basic drawing, we're going to just do them in straight here. A straight line. So we're going to set them a wee bit narrower and we're going to set them to red. So we're going to draw them on here now and just select a point. So we'll start here with this blade to the control ring. This blade at this point to the control ring. This blade to the control ring. So an important feature of this design is each of the blades have a main pivoting point on the body enclosure of the system for this mechanism to work. So I'm just going to draw this pivoting point. So say about here, here and here. So when the big black ring rotates now, the blades all turn on the hinging points as the red control arms push or pull the blades, opening and closing the aperture or the diaphragm. Okay, so let's say I did design my aperture to the same spec as the illustration I just covered, or by having the same mechanical technique as your typical camera aperture. I would have required advanced machining, that being CNC milling or laser cutting, depending on the design of course. So that would have been moving away from fabrication and towards more expensive materials, machining. Also, a larger number of additional parts, equal sized adjoining linkages, plates would have been required. I honestly could have done it this way. I could have fabricated each part by hand, although this would have been very time consuming as each arm needs to be identical in order for the actual project to work as this animation is working. So in the future I will build a bigger aperture this way with the control ring, and I will compare it to my unique design seen here on screen with the HTD belt and also the HTD pulleys, the gears. Okay, so before we focus on the actual design, I want to touch on a couple of important features that have an impact on the timing and the physical appearance of my aperture project. So normally with your typical aperture linkage control mechanism within a camera, additional parts are required as the number of blades are increased to form and control the diaphragm, as you'd expect. So I'm talking about this from an engineering perspective. So if it were to be engineered on a larger scale is what I'm trying to say. This is also the case for my system here. So if I increase the number of blades, I'm increasing the number of gears or pulleys. If I increase the number of gears, pulleys, I'm increasing the number of shafts. If I'm increasing the number of shafts, I'm increasing the number of spacers, brackets, bolts, everything. So it's very much the same as your standard aperture. So throughout my design, I have kept creativity in mind, as the entire diaphragm and its mechanical mechanism are on display and are not hidden by obstructing components, such as a large control ring. This makes the system very appealing as it possibly can, without affecting its performance. For example, these gears would be beneficial turned around facing the enclosure surround, allowing the timing process to be much more efficient, although I purposely set them this way to show the mechanisms of the aperture. So in other words, the diaphragm would be easier timed with these gears and bolts facing outwards towards the interior side, where I have increased the level of difficulty here of the timing system by having these facing the exterior side. So I say increased difficulty. Let me rephrase that. I have increased the level of difficulty enormously with this visual adjustment in place, where I will discuss the timing process soon. The trade-off is worth it, in my opinion, as you will see in part 3, the masterpiece itself. It's very attractive, where all the gears can be seen in operation, but are also seen throughout the reflective double-sided mirror polished finish. So I'll do a wee view here at the other side again. So this is all mirror in the actual piece, the masterpiece, inside and out, and you can see everything working in the reflective finish. You can see the gears all reflected in the side, so it's a really attractive and appealing looking project. Okay, so from this point forward, I'm going to discuss my design and my design only. So here I will focus on prototype 1 as I have been doing, then I will gradually follow on to prototype 2, which becomes more interesting. So, to clarify, the drive mechanism, the tensioners and also blade design were all entirely different in the final prototype compared to the earlier design. So both prototypes were always similar in that they had more than 500 pieces, 500 parts. So this figure includes all the produced parts as well as the additional components and also all the stainless steel fixtures, such as the bolts, the nuts, the washers, and other concealed parts not seen in the assembly as they rest below other parts. So in the latter moment of this video, I will demonstrate an assembly breakdown and exploded view to view everything in more detail. Okay, so just a little example here before we focus more on the Aperture's mechanical mechanism. So if I scroll around to the enclosure we discussed earlier, we can see clearly that it's made up out of 3 pieces of sheet steel. 1, 2 and 3. So these pieces have been formed and welded together where they are only recognised as one part within the assembly. So the front face is welded to the outer sidewall, and the same front face is also welded to the inner sidewall. So this provides me with a sturdy structure required to contain the Aperture's entire control mechanism. Another example here of an alone part would be each one of these blades and the diaphragm, and also each one of these upper brackets. So hopefully this helps everyone understand how many components are actually in the assembly. So there's a lot going on here, more than meets the eye, but I shall discuss this in more depth later on in the video. Okay, so for this next stage I'm going to unsuppress the enclosure's lid and its rubber trim, bringing them back into play, making the assembly complete for this next discussion. So if you previously recall, I suppressed these components to hide them from view earlier in the demonstrations, so we could see the workings of the Aperture, or the internal mechanics of the Aperture, shall I say. So over here in the design tree, I'm going to unsuppress these components. So the lid and the rubber trim. So that's it done now. So I'm going to now set these covers, both the base enclosure and the enclosure's cover lid, to transparent to expose all the internal mechanics of the Aperture. So I'll do that now just. So both these parts are still visible in the assembly, only we can see through them this time. So as shown in the model, there's 18 of everything. For example, there's 18 blades that make up the diaphragm. There's 18 gears for each one of the blades. There's also 18 shafts for each gear to spin on, and also 18 lower brackets, 18 higher brackets for each shaft to be mounted on. And the list goes on. So there's a lot there, a lot of components. So if we look closely at this assembly of one of these blade mount locations, so if I zoom in here, we can see that the blade is centered between the exterior and the interior faces by means of these little upper and lower spacers. So I'll zoom in even further here. So we have the lower spacer at the side, and we have the higher spacer at this side. Okay, so if I again select one of these blade mounting positions and zoom in for a closer look, I'm going to select the one here at the top, away from this actuator at the bottom. So if I go way up here at this point and zoom in nice and close, we can see a nice clear assembly of components. So this lower bracket is fixed to the base enclosure using two dome head M6 bolts. Also, this top bracket is fixed the same way. So at the bottom of the gear we have the lower spacer, and at the top of the gear we have the upper spacer. So these spacers are there, as I mentioned, to keep the blade centralized to the two faces of the Aperture. So if I was to set this lower spacer to transparent and also this upper spacer to transparent, we can see the shaft which the gear spins on. So if I was to zoom in even closer here to this shaft, if I set this shaft to transparent, we can see the fixture, which is a stainless threaded stud which is attached directly to this lower bracket. So this threaded stud holds the shaft, so the shaft is threaded on the inside, and also at the top of the shaft it's threaded at the inside, which the countersunk screw protrudes down into it. So the countersunk screw tightens into the shaft, and this whole assembly is held in place. So there's an important feature or an important component here within this assembly that I never mentioned. So if we look here at the bottom of this gear, a low friction thrust washer made of a metal composite self-lubricating substance is sandwiched between the lower spacer and the gear. But also the gear and the higher spacer has the same little washer in between. So you can see here there's also a little washer, thrust washer sandwiched between the upper part of the gear and the upper spacer. Okay, so I forgot to mention a crucial feature of this gear assembly. So if I scroll around here and pick a position, so I'll pick it one at the top again. So this gear assembly here, we'll focus on this. So if I were to set this gear to transparent, which I will do, we can see a special component lies between the shaft and the gear. So this bush is in place to reduce friction between these two mating surfaces. So these bushes were pressed into the gears and are of a similar high quality or high grade centered porous material, but this time they are bronze. So I have impregnated these bushes with oil after the powder coating stage. So everything works together, all these special components work together to make this unique project work. Okay, so unlike other apertures of this size that you may come across on YouTube, all of the parts throughout both prototypes were handcrafted rather than machine focused. So you could argue that I'm telling a fib here. So I obviously didn't sit down and cut all these blades within the diaphragm by using a grinder. These were actually cut using a specialised laser machine to maximise the overall accuracy of the project and to remove the rough edges that you would get using power tools. So this allows the diaphragm to operate much more smoothly, similar to this 3D model. So after the cutting process, the 18 blades were then hand polished on both sides, as were all of their surrounding edges. This in turn reduces the friction within the diaphragm during operation, whilst also it enhances the visual look of the system. So when I say everything was handcrafted, I mean the enclosure's lid, and all of the 36 brackets, including the actuator mount brackets and all the advanced parts that will follow in Model 2, Prototype 2. Okay, before we move on, I want to take one final look at the 36 brackets surrounding the enclosure for the mounting of the 18 shafts. So these brackets are very important throughout the entire assembly of the Aperture. They need to be strong, they need to be durable, and they also need to be accurate. So I have knowingly set the bottom bracket grip to yellow here, and the top two bracket grips to red and green to benefit this discussion, where these coloured grips signify the bracket type and also their location. So the yellow brackets are all the same, where no differences exist within the grip, so all the lower brackets are identical. So if we scroll around to the interior side, both the green and the red bracket grips are similar with one difference, and one difference only, where the red brackets have an extra tapped hole for the cover lid attachment. Also, notice how the top bracket grips are evenly spaced out, red, green, red, green, red, green, and so on. And also notice how each one of the countersunk holes is positioned in an identical manner on the end of both these bracket grips. So if I draw a line from the centre of the aperture to the centre of each countersunk hole, these lines would have a matching dimension required for this systematic system. Importantly, each one of these countersunk holes align up with the threaded studs in the lower brackets seen here. Interestingly, these 36 parts were manufactured using a small metal former bender appearing on the screen now. So this device was built specifically for this project with custom V-dies made from nylon blocks to eliminate marking on the mirror polished flat bar whilst forming. So this project has been previously demonstrated on my channel, and the link is in the description for this small flat bar bender. So if any light marking did occur in the mirror polished finish of these flat bars, it would have been better than metal to metal scoring or gouging, where more effort would have been required in the latter stages. So these blocks were designed and created to decrease the work required in the final stages of polishing, as the tarnished, stressed edges needed to be polished after bending. So this special metal former was made for this purpose and this purpose only. In addition to this, all these upper and lower brackets were drilled using custom jigs appearing on the screen now. Because of the finish I desired, a lot of extra work was required in this project. Okay, so now that all those important aspects are pointed out, I'm going to keep talking about this earlier design for now. So we're nearly there, we're nearly ready to jump ship, moving on to prototype 2 soon. But first, let's continue here. So, this earlier prototype was designed around a single-sided HTD timing belt at 2,800mm long. So the width of the belt was 20mm and the pitch between the teeth was 8mm, where both the belt width and the pitch has stayed the same in prototype 2. The major difference in prototype 2 is the overall length of the belt, which has increased significantly to over 3 meters. So I think it's approximately 300mm longer or 350mm longer. I will talk about that later. So here the belt is seen to circulate the entire surround of the enclosure, passing around the 18 gears and the tensioner at the bottom. So keep in mind for this discussion, all the parts within the model are all dependent on each other and are fixed together using a selection of stainless steel fixtures. So my design requires on-point timing, which is achieved at the underside of the blades using a specially designed timing tool appearing on the screen here now. So basically you place or position the tool, the special tool, down between the blades from the interior side. Then you proceed to slacken the two bolts seen there at the bottom of the blade below the gear, and then you move the blades into position. You time the blades, then you retighten these two bolts to finish the process. So if you imagine this base enclosure being manufactured from a weaker material and not the 2mm stainless steel which I have selected, there's a chance it could distort or even buckle or crumble from the stresses, strains and forces exerted on it by this drive belt. For example, if the enclosure was manufactured out of 0.9 or even 1.5mm stainless, it's very likely that this design will not handle the alternate forces within the drive system or the high tension that's required on the large belt to keep the system in sync. So the blades' weight with respect to their timed orientation at the specific point of movement on the enclosure surround or their dynamic position on the aperture are all distinctive for the system to work. So basically once the system is timed, there will be a top and bottom of the aperture, the bottom being established with the position of the actuator rather than having the additional weight at the top or even the sides. So we know already that these blades within the diaphragm are manufactured from stainless steel metal, which has increased difficulties with friction when passing each other, especially at the closed and opening positions when the blades tend to overlap near the shaft mount points and at the aperture pupil of the system. So the centre of the blades and also when the blades are fully retract into the enclosure. Hence why there's only 2 bolts at the back side of the blades to allow the adjoining blades to float or to spring where they need to spring, reducing the stresses here. For example, if I were to use a thin flexible ABS material here, things would be much easier, but I choose to keep the aperture purely stainless steel for the mirror finish I desired. I know we've briefly touched on the diaphragm throughout, but now looking at it from a different angle here. Okay, so these blades together, as we know from brief discussions earlier, forms the diaphragm that serves as the aperture stop, providing the varying aperture sizes. So this diaphragm functions much like the iris of an eye, as it controls the effective diameter of the lens opening. So see part 1 of this project for more information on my channel if you haven't done already. So I have put the link in the description for that video. In that video I discussed different similarities between the eye and the camera aperture. So the diaphragm seen here is designed to have 18 blades and is designed merely on the overall size and the quality of the aperture whilst having cost in mind. So the narrower the blade is, the more blades would be required to close the same size of an opening aperture space. Likewise, the broader the blades are, the enclosure becomes less complex, less expensive, less attractive, and less appealing. For example, with broader blades, how would we hide them? We could use a bigger, more obstructive enclosure, which would be less appealing. So a trade-off by having less parts, blades, would be cheaper and less complex, but a bigger surround compartment would be required to hold the blades, making it less compact. My goal was always to keep the aperture surround as compact as possible, in this case to give the viewer the thought of illusion. So you can see here how the diaphragm fully retracts into this enclosure at the front face and at the interior face, the interior side. As mentioned earlier, these blades in this project are designed to be curved, to blend or fall back into the compact enclosure or the surround seen here. So if these blades were straight, it would result in a definite polygon shape at the diaphragm's opening. Therefore, curved blades improve the overall roundness of the iris opening seen here. This allows a much better opening for sight, light, airflow, or even space to maneuver your body through it, or to pass an object through it, benefiting the use of an aperture of this caliber. Hence, this diaphragm is also capable of reducing or increasing the amount of light or air that hits the detector by altering the aperture size. That being if a detector was at either side of the aperture. So let's say I did go with bigger blades within this prototype's enclosure. In the closed state, we would see a larger polygon shaped opening. Likewise, in its open state, we would have a smaller opening, whilst also being of a polygon shape. So it would be less round and it would be a much more coarse opening, making it more destructive for anything passing through it. For example, it could create turbulence if air was forced through it. Also, a larger enclosure would be required to hide these broader blades from view. So, one thing I never touched on throughout this entire lengthy process, this discussion process, was the preset angle that the shaft, the axis, the shafts sit on. So each of the 18 blades rest slightly on each other at an offset of approximately 1 degree on its original axis. So the shafts are preset at 91 degrees off the front face to benefit the diaphragm's operation. So if anything was too rigid within this assembly, where it needed to flex, we would have major flaws throughout the system. So there's no margin for error within this design. Also, a vast number of varying stresses and forces on the entire structure is quite mind-boggling, but are all required for this large aperture to work. As there's no timing belt in your common aperture or any apertures that have been created on this scale on YouTube, these same stresses do not occur in this manner. As demonstrated throughout, there never appear to be any issues with Prototype 1 during all the motion studies seen throughout the detailed discussions. However, major flaws occurred during the initial testing of Prototype 1. So when this actuator seen at the bottom of the actual diaphragm here was powered up, controlling one of the gears seen here. The other 17 gears became out of sync, with the one being directly driven by the actuator. So there was excessive spring in the drive belt between the driving gear and the gear to the right or left of it, depending on the direction the belt was moving. Apart from this major glitch, it was good to see the other 17 blades following closely in sync. So this gives me hope that I might make something out of this project yet. Otherwise, in all honesty, the project would have been scrapped. From this point forward, I knew exactly what needed doing. I just needed the 18 blades to work together, supporting each other at the overlaps in a balanced technique, but with more power and more speed. With this all in mind, major changes were needed at this point. Okay, so before I move on here to the second and final prototype, I'm going to cover some interesting facts from the initial Aperture design and the manufacturing stages leading on to the second prototype. Okay, so for this next part, I'm going to go over a few interesting facts of the earlier design stages. I will do the same process for prototype 2 once I have the final discussions complete. Just keep in mind, some of these facts apply to prototype 2 as well. Okay, so if one bracket was released or slackened, the entire system would become affected and the timing of the aperture would be off by a large margin. So the iris opening seen here, the aperture, the hole, would more than likely become an oval shape. In more detail, the direction of force applied at each gear by the belt is pulling into the centre of the enclosure. Therefore, the enclosure's negative force at the upper and lower brackets is equal to this, making it stable. If the enclosure was unstable, not balanced, weak or poorly designed, the force on these gears would crumple the entire structure. So there will be no consistency even in static motion, not to mention during complex dynamic motions. Another interesting fact here, timing the project is like timing a car engine with 18 pulley gears whilst not being able to see the bolts, but using the mirror finish to guide me with a special homemade tool. I also forgot to mention earlier that these gears are engine crankshaft gears, timing gears, that I specifically selected from a 1990 Volkswagen Golf that were all purchased from Volkswagen in Germany at the time. Okay, we have 4 interesting facts left to rattle off before we move on to prototype 2, which becomes very interesting. So, this system could be used as a futuristic door, or even a window shield, or even as an industrial louver system, where it could be scaled up or down to suit its purpose. I can imagine my house in the future full of round windows with these as automatic fancy blinds. So if you can imagine this aperture for a louver system, there are 0 restrictions to flow, no areas for grease or overspray to cling to as the blades are tucked away in the surround of the enclosure. Also, the system could be used as an airflow regulator. So in earlier design, each of the 18 shafts were perpendicular to the enclosure's front face. There was quite a bit of unwanted stresses and binding issues during the opening and closing cycles within the diaphragm. So the final fact here, the 2 fancy actuator brackets appearing on the screen now and seen here in prototype 1 were handmade twice. I accidentally travelled to my local shop with these on the roof of my car after giving them the final polish on the 6th day of manufacturing, where they were never seen again. So now moving on to prototype 2. I hope everyone enjoyed this in-depth discussion. It will now get more interesting. Okay, so here we go. Seen on the screen is the final model for the final prototype, where I have already set everything transparent to show the mechanical assembly in clear detail. This assembly is lagging a little due to the amount of components, the amount of detail that's in it, so please ignore the jitteriness seen here. You could say the Aperture is a little nervous revealing itself. Because of this, I will create a MP4 video file for a clearer, smoother illustration of the animation, and I will attach it after the discussions are complete. Just like the earlier prototype, this is where the blueprints were extracted from for the final manufacturing stage. Also, like prototype 1, there are over 500 parts altogether in this final piece, but a little more here due to the advancements of the project. The enclosure, the bushes, the gears, the spacers, the shafts, and all the brackets were not changed at this point. The main differences here are the altered blades, the mounting of the blades, the tensioners, and the entire drive assembly and the blue platform seen at the bottom here. We will look at these in more detail soon. So due to the glitches within the first prototype, this new prototype was redesigned completely in my head. I have now decided to drive the belt using a wheelchair motor and gearbox rather than moving one gear and expecting the other 17 gears to replicate the same movement instantly. No matter how much tension was applied to the belt throughout prototype 1, there would always be unwanted spring between the driving gears due to the excessive rotating force needed to provide movement of all the diaphragm. Okay, to make these changes all work, I needed to obtain another HTD timing belt, a little longer this time, as not only did I decide to use a wheelchair motor and gearbox to drive the belt, but I also decided to tension the belt with the same unit rather than using an additional adjustment tensioner. So it's very important for this belt to be extremely tight to reduce belt slippage, as the belt only rests upon 3 teeth of each gear, owing to the close proximity of neighbouring gears along with the large belt circumference. So first things first, I'm just going to go back here to that comment I made about the gearbox and how it pivots and how it adjusts the belt. So if I zoom in here to this point, we can see that the gearbox shaft and the gear goes in between 2 of the gears to tension the actual belt of the diaphragm, the aperture. So if I go round to the front again, so I have the gearbox mounted at this point, so it's pivoting here at this bolt, this Allen key head, so it's pivoting here. I think it's an M10 bolt as far as I mind, and at this point then, so if I was to grab the back of this motor, this gearbox, and move it in towards the centre of the aperture, I would be in turn tightening this belt. So that's a really unique way of tightening the belt without using additional tensioners. Okay, so going back to the belt here, the way it rests upon each gear. So if we look closely here, we can see, well, obviously I haven't got the teeth drawn into the belt. I've just got a band drawn to simulate the belt on the aperture. But if you look at it closely here, due to the close proximity of the other gears and the large circumference of the actual aperture in the belt, we can see that only 3 teeth will be on the gear at any time. So that's important for it's important for the belt to be tight. That's really important, so you don't want the slippage or the whole thing will go out of timing. Okay, to reiterate, the first prototype was designed around a belt with a length of 2,800mm, where with this new prototype I needed an additional 75mm approximately to fit around the new gear on the gearbox and in between the two neighbouring gears. So what I'm going to do here is I'm going to focus on the new area, the new mechanism of the Aperture by setting all these new components and parts to transparent. So we're going to focus on it here first. I'm going to set the gearbox to transparent, this platform to transparent, and this will allow us to get a look at what's going on underneath. So I'm going to run the motion study again. Okay, so this timing belt seen here is now switched to a double-sided belt at a new determined length of 2,875mm, which is required as we are now working on the other side of the belt. This design allows pre-adjustment by mounting the motor and the gearbox at an adequate angle with respect to the motor shaft and the neighbouring two gears. This belt size also couldn't be sourced or anything near it worldwide, but we will get into that soon on how I overcame this. For now, let's keep focusing on this end of the Aperture. A new platform base seen in the blue was created using an aerospace grade aluminium to support the new driving mechanism and strengthen the area where the heavy duty high torque motor is mounted. So I will do a nice angled view of this platform base, the motor and the gearbox to get an outlook of how it's all mounted to the Aperture. So this motor gearbox unit was removed from one of the biggest high performance durable wheelchairs that's available on the market, known as an Infocare TDX. So strength throughout this part of the assembly is important to handle the excessive rotating forces required to provide movement of all the diaphragm. So within this area of the assembly, I have taken advantage of 4 of these bracket mounting points to balance out the rebound forces, the stresses of the new motor, where they are evenly spread across the enclosure or this area of the system. So I'm going to set this back to plan view here. So I'll have to stop maybe. No, I don't have to stop it. So we're going to bring it up here. And we're going to look down on this platform base, this blue item here. So I'm going to stop the motion study for the meantime. And I'm going to set the gearbox to transparent, the motor to transparent. And I'm just going to give one final wee discussion here to finish this part off. So here you can see the 4, if I was to click at this point, and underneath this bracket we have another bolt here, and we have a bolt here, and we also have one here. So these 4 bolts are new countersunk bolts attaching the platform to the sturdy tap shafts, where the 4 bolts pass down through the 4 upper brackets existing holes. So what I have done here is I've removed the bolts that used to hold the shafts to the brackets, and now what I'm doing is I'm going straight down through the brackets and into the shaft. So it's quite strong the way I've done this, quite sturdy. Okay, to finish off discussions around this part of the system, there are 2 new important brackets seen here that are attached to this new platform. So the one on the left here, would I stop this motion study a wee minute? The one on the left here and the one that rests below the gearbox. The one that hides below the gearbox, shall I say. So I'm going to set this platform to transparent for now to assist with the discussion of this tensioner and this mounting bracket. So I will focus on the stainless steel hinging bracket highlighted first, then we will move on to this tensioner bracket seen on the right. So this stainless steel hinging bracket looks pretty much like a bollard, which allows the gearbox, the motor, to pivot in and out from the center of the aperture. So if you can imagine, it's pivoting on this point. If I was to grab this motor here at this point, I can move it, what do you see, in and out, like so. So now that I've discussed how it works, I'm going to discuss how it's fixed to the platform. So the bracket is directly fixed here using a M10 cap bolt at this end, which protrudes up through this platform and into the tapped hole of the stainless steel bracket. At the other end we have an M8 bolt which is fixed directly to one of these shaft mounting points that I discussed earlier. So this is one of the strongest points of the aperture, keeping in mind there are 17 other similar points. So I'm going to set a couple of these components to transparent here to assist with this discussion too. So if I can highlight this bolt, there we go. So this bolt goes down through the new bollard type hinging bracket, through the new platform base, through one of the upper brackets we initially discussed within prototype 1, and into the tapped shaft where everything comes together as one. Okay, it seems the motion study is lagging a lot more than expected with this model. So to reduce the jitteriness seen throughout, I have slowed the shutter speed, the diaphragm speed down. I will attach a few MP4 video files as discussed at the end of this video to demonstrate a smoother operation of the system. I do think it's best to keep the diaphragm moving throughout most of these discussions as it keeps the assembly interesting. Okay, to discuss the second bracket in this area, I have set the blue platform base plate back to its original state. Therefore, we can no longer see through it to the underside. For this part of the discussion, I am switching both parts of the gearbox, the gear casing and the lid to transparent to focus on the bracket of interest which lies underneath the gearbox. So I have to stop this motion study for this next part. Set these two components to transparent. And we'll zoom in even closer here. So the bracket highlighted is a specially designed belt tensioner which is also made up out of stainless steel and is fixed to the platform base using a countersunk bolt seen in the centre of the bracket and a washer lock nut at the underside of the platform seen here. So I'll highlight the nut here. There's the lock nut and the washer sits above it. So it's important that this countersunk bolt is not overly tightened as the mounting point lets the bracket pivot and glide on the anodized platform, allowing the gearbox motor to float and to be fastened in place. I will do a wee demonstration here to show the tensioner mechanism in operation. So if I grab or select the motor here at this point and move it inwards and outwards from the centre of the aperture, we can see how this tensioner bracket glides whilst the adjuster stud makes use of the slotted hole during the adjustment stages. Also, notice how the gearbox pivots on the bollard type hinge bracket to the left of it. So I will do a wee plan view here of this demonstration to show this in better detail in plain view. But first I have to set this gearbox back to its original state. So I'll bring it into view here, looking down on it. Okay, so if I grab the motor at this point and move it inwards towards the center of the aperture and outwards towards the outside of the enclosure, we can see this bracket gliding on the anodized platform. We can also see the bollard type bracket to the left of it supporting the gearbox motor, whilst also allowing it to hinge and pivot. So if I wanted to tension the belt, I would move the motor inwards towards the center of the aperture, and if I wanted to slacken or retract the belt, I would move the motor out this way, away from the center of the aperture. To clarify, if I wanted to add more tension to the belt or retract the tension of the belt, I would adjust these two nuts correspondingly. Once the large belt is tensioned using the adjuster highlighted here, or when I find the perfect tension of the belt, it is then locked at this point, bringing these two nuts together. Okay, now that this is all covered, I am going to focus on a smart, interesting mechanism on the other side of the aperture. So, existing brackets that were initially used within Prototype 1 were reused, adapted to suit other parts of the aperture within this model, Prototype 2. For example, the stainless steel mount appearing on the screen now, used to hold the linear motor of Prototype 1, is now used as a fixed tensioner appearing on the screen now and seen here at the top of the model. The tensioner is used here to compensate for the larger belt size that could only be sourced at 3048mm, which was 75mm too big. Therefore, its main purpose is to remove a bit of belt slack, approximately 75mm, but it works well as it pushes the belt into the center of the aperture, just as the gearbox motor does on the opposite side, 180 degrees away. If we think about this for a second, this benefits the system in other ways. It balances out the tension of the timing system. For example, if this tensioner wasn't here, the timing system would depend on the tension created on the belt from the gearbox side, which is further away. Hence, the further we move away from the gearbox side tensioner in theory, the pressure on these far gears will become less. For example, the large circumference of the belt, with all the stress and strains, along with the additional forces, could cause the belt to stretch. Therefore, by pushing in on the belt at this point, it will benefit the assembly dramatically. So I'm going to just stop this motion study to continue on here. I'm going to focus in on this tensioner. Okay, so to use this existing bracket highlighted, so when I'm saying bracket, I mean plate that's removed from a bracket on Prototype 1, reinforcement was required, seen below the plate, to support the excessive forces on this HTD freewheeling pulley to make sure it doesn't buckle under loads. Also, This reinforcement helps make sure that this new tensioner part is mounted in the best way possible, so that the force applied to the enclosure is spread evenly across, seen by these flat pieces of 6mm stainless steel. So I'm going to set this plate to transparent here to just get a look at what's underneath exactly. So we have this 6mm plate here, which is about 100mm long, 50mm wide. We have, I will set it transparent too, to show the shaft. We have the shaft, which is welded directly into the stainless steel plate. We also have another stainless steel plate which goes down the back to support it. We have these two M6 bolts, domed head bolts, which fix the tensioner to the base enclosure. So that's really it. So the plate at the top here, the handcrafted creative face part with all the holes, is really just placed here to hide this heavy duty stainless flat bar used to support the gear. But it also assists with the adjoining plate that bolts to the enclosure with the two M6 bolts seen at the rear of the tensioner here, as I've mentioned. So that's it. I'll just undo this last move here to show these parts. So it looks quite well, this little piece. It works really well too. So just a wee view of it from this side here, the underside. So you can see there that this flat bar and this flat bar are welded together in the real masterpiece, and these two plates are perpendicular to each other, so that the gear is sitting flush with these gears attached to the blades. Another bracket that was made for the first prototype was also reused, adapted to suit a new part required for the Aperture, that being for the current prototype 2. For example, the stainless steel bracket appearing on the screen now was used to maneuver the single gear driven by the linear actuator in prototype 1. This was modified, appearing on the screen now, but also seen here to the bottom right hand side of the Aperture, near the new motor's platform plate in this location. So I'll zoom in here. So this bracket was adopted to act as a limit switch detector plate for prototype 2, which is used to determine what state the Aperture is in, open or closed. It is fixed to one of the gears using two M8 threaded studs. So I'll get a wee side view of this here. So you can see the two studs here. I'll zoom in nice and close. And it's also fixed using 4 washers and 4 nuts. So this allows fine adjustment of both height and the angle of orientation. If you focus in on this detector plate even more here, you will see how both roller levers of the switches align up with the 2 notches in both its open and closed state. A little interesting fact here, from fully open to fully closed, this plate is rotating 46 degrees, no more and no less. So I'm going to just zoom out here to show these 2 notches, and I will bring the Aperture into a nice view. So if you look at this now, in open state you will see one of these switches aligning up with the notches, and in closed state you will see the other switch aligning up with the other notch. So open there now, the right switch, notch aligned to the lever. Closed here now, notch aligned to the lever. Works really well. So 2 additional brackets were added to the enclosure seen at this new detector Aperture positioning plate to attach the new opening and closing limit switches to the left and right of it here. As seen with these brackets, these switches can be adjusted to set the Aperture's maximum and minimum open and close states by moving the switches on the slotted holes. In other words, altering the angle of orientation spoken about, increasing or decreasing the 46 degrees range of the diaphragm. Also seen in this area of the aperture is a miniature 8-pole connector, mainly for the attachment of these very important limit switches. So I have specifically placed this connector here to keep the wire lengths minimal leading to these switches, where this directly connects using a cable to a control module I created for the system, which I will demonstrate in part 3 of the project coming soon. Within the masterpiece that will be presented then, all the wires are directly soldered to the connector's pins, just passing the underside of the timing belt. So I'm going to stop this motion study here to give a better discussion of this connector and why I located it here. Okay, so it was important for me to keep this connector in the center of the two shaft mounting brackets, but also in the center from the top to the bottom of the enclosure for a better visual look, or so it didn't spoil the look of the aperture once it was complete. Because of this, I was met with the connector's wires skimming the lower end of the timing belt seen here. So if I zoom in nice and close here, you'll see that. So this is because of the compact nature of the system. So when I say skimming, not exactly touching, but approximately a 5mm clearance gap. However, this was okay as the wires were focused down towards the inside face of the enclosure, away from the belt. Also, this connector allows the connection of a multi-functioning LED interior light that is hidden below the blades around the inner wall of the base enclosure to show the aperture off. So when I say inner wall, I'm talking this point here. So you can't really see it, but below this blue bead here at this point. So you'll never see the LED strip light because it's hidden below the blades and tucked in behind this wall. Okay, so this will be presented within the masterpiece where they light up and bounce off all the more finished parts, which really does look spectacular. Also, the motor has its own high current 2-pin miniature plug connection, which is fed directly back to this control module that I have created. So it's not shown here. So it's not directly connected to this connector, as it's kept for the low current circuits only. So it's an 8-pin plug, and I think there's only 2 spaces or 2 pins left. Okay, so I think I've covered everything I need to cover to this point. I just want to finish off these discussions before moving on to the interesting facts of Prototype 2 by pointing out one final new feature part of the Aperture. You may have noticed already, the stainless steel base enclosure's lid was adopted and made to fit around the new wheelchair, motor and the clever anodized platform. To view this, I will set the enclosure's lid to its normal state. Okay, here we can see this cutout section that fits around the new platform base, completely changing from the first prototype where a hole cutout and bulge was visible for the linear motor. So I'll do a wee view at the side and then I will open the part. Okay, so I have the part opened here now. So we can see this unique cutout section and a nice clear view here now. So it fits quite well. Okay, I'm going back to the assembly here now. Okay, so other additional modifications might be made in the future by adding a stepper motor to control and keep track of the varying diaphragm, the f-stop positions. Okay, so for this final part, I'm going to go over a few interesting facts of the design stages of Model 2, Prototype 2, just as I done with Model 1, Prototype 1. Some of the information may have been mentioned before, but I will make this procedure quick. Okay, so first fact, if the Aperture system was timed on its flat and then it was positioned vertically on a stand, the Aperture iris will become slightly oval, just like the shape of an eyelid. To fix this, the project needs timed on the viewing stand that will be presented in part 3, or timed in its newly mounted location. This is due to the sag on the belt caused by the weight of each blade that varies due to the position on their hangers, the gears, but also dependent on the other blades' positions in the surrounding enclosure. So it's all very complex here. Okay, so next fact, the two fancy linear actuator brackets seen in Prototype 1 were handmade twice. I accidentally travelled to my local shop with these on the roof of my car. I gave them the final polish on the 6th day and set them in the sun, never to be seen again. I think because of this doubling effort here involved in the early manufacturing stage, this is why I utilised them in the way I did in the final prototype, which they turned out to be exceptional for the task they were used for. Okay, so a few facts around the base enclosure. I have set the enclosure to red to assist with this discussion. Okay, believe it or not, the enclosure was made 2 times. The first time I hand polished the lot, both sides, it got damaged due to the tweaks made in the later stages, so there was quite a few scratches during the experimental stages after Prototype 1. Then my OCD kicked into overdrive. More holes were also required on the surround, and some weren't required due to the changes in the second prototype. Once I got the Aperture working away from the model, I knew exactly what to do the next time. The second time I used one-sided Moore grade 316 stainless steel, polishing all the faces before welding off the inner and outer walls. Okay, so one final fact on this. Whilst completing initial 3D modelling and motion studies, the stress and strain issues were not recognised on the enclosure. This is where the new anodised blue platform came to play, strengthening the area where the drive mechanism was located. Okay, so I have quite a few facts around the blades. I have also set the blades here to red to assist with the discussion, where they are still set to transparent also, which is good. As you can see clearly, the blade overlap in the dark red and the part not overlapped in the faint red. Okay, so the first fact being the blades were reduced from 2mm to 0.9mm thickness to relieve stresses during Prototype 2 to allow more flexibility within the system. Also, the blades were altered to remove the square corner at the opposite side of the hinge point, the gear side, to reduce unnecessary contact causing drag or binding issues, where everything tended to be more rigid in this area. If you remember in Prototype 1, each one of these blades had a square edge here, which caused a lot of binding issues with the neighbouring blades. If we think about this with respect to this demonstration, there would have been too much contact areas in the dark red if the blades still had this excessive material. If you follow each one of these blades in the assembly, you will see a special curved notch, a cutout, which is there to allow the blades to fully retract into the neighbouring gear assembly points, allowing the diaphragm to fully open. Also, the blades of the masterpiece have several 25mm vinyl circles placed over both the faces evenly to reduce drag between them and to reduce marking of the mirror polished faces, which is not seen here in this model. Also, from prototype 1 to the final prototype, 2 bolts were removed to allow more flexibility of the blade within the diaphragm. For this last part, I'm just going to finish up by looking at the final 3 interesting facts. Okay, so each one of these 18 shafts was never perpendicular to the base enclosure in prototype 2. There was always a 1° angle across all the shaft assemblies in the same direction to allow the blades of the diaphragm to mate better through the opening and closing cycles. After the teething problems was visually seen throughout prototype 1, prototype 2 was completely planned in my head, not dependent on any 3D models. Therefore, both the final prototype and the final model were reverse engineered from the first prototype, not dependent on the modeling software. Hence, the final model only came after the final prototype was complete. Okay, so one last interesting fact of the system. A microcontroller was programmed to take care of the aperture direction, the shutter speed, and the aperture's limits. Okay, so that's it complete. We are finally here, and I hope everyone enjoyed as much as I did. As promised earlier, here's a smoother motion analysis of prototype 1. It contains multiple views of the Aperture's diaphragm, opening and closing, showcasing the components I highlighted earlier. Most importantly, here's the final prototype that also includes a smoother motion analysis of the Aperture's diaphragm opening and closing, and a variety of views of the finalized components I mentioned earlier. As also mentioned, here is a breakdown of one of the gear assemblies. Okay, so that's the video complete, and I'm sure I've talked about everything. I've left no stone unturned throughout the design stages. I didn't think I was going to cover so much detailed discussions. I actually lost my voice at one stage, I spoke that much. I hope you enjoyed this video. Please hit the thumbs up if you did. It's a project that I've been meaning to cover for years now. If you want to see this project evolve throughout the next part and to see other unique and interesting projects, please subscribe and hit the post notifications bell to see the latest from my channel. So thank you for watching everyone, and goodbye.